All right, so it's recording now. So as I said, what we're going to do is just go over word problems. So for that, we are going to, I need to share probably. Just going to share the main screen. And we're going to navigate to back to Brightspace. Yep. And then if you remember here, let me just do this real quick. This intro, remember, has these NumPy examples, right? It'll take you to a link. So what you have to do is do all those, okay? Type them up on Jupyter Notebook, run them. And then it's gonna, so you're gonna write the code, and then you're gonna get the results, right? Start doing that. This homework assignment won't be due next Monday. Instead, it's gonna be due 2 weeks from today. Okay, but start working on it. Got it? Any questions on that assignment? No? All right. So just start working on it. Next Monday when we meet, I will look it over just to make sure everyone's doing well with it, but that's basically it. All right. The second module is this one, machine learning, and just thinking about word problems, okay? So here I have a couple of documents. So I think if we click on this, it'll open. Yep, there we go. All right, so we'll be using this. Oh, there we go. All right, so yeah, so I have 5 problems here, right? So very simple word problems. And I'm going to use the electronic whiteboard here to kind of, start thinking about it. How do you translate problem into a machine learning, and to the information that you need for machine learning, okay? So let's go ahead and do the first one. So here the homework is like this. So the problems are going to be for the following, and these are classification problems, which means, is this a cat or a dog? Is this an intrusion or not an intrusion? Identify and or define the following. So this is what I'm always looking. What is the X matrix? What is the Y vector? What are the samples? What are the classes? Define a set of features, define the dimensions of X and Y, and indicate what they mean. If you answer those questions, you're in good shape towards solving your machine learning problem, okay? Because this starts to tell you what the data looks like, the format of it, what algorithm you're going to need, how do you collect the data, etc. Okay, just by answering these few questions. So let's keep that in mind. Okay, so I have several problems here. Number one is a classification model for finding guns in images posted on Facebook. Okay. Number two, a model that detects if automatically generated text is biased towards certain categories of people, such as based on ethnic background. Number three, a classification model for movie recommendation, e.g. Netflix. Number four, a classification model for weather monitoring. And number five, a classification model for cancer diagnosis using 3D image scans. Okay, so let's start with the first one, a classification model for finding guns and images posted on Facebook. So we know the data is what? Images, right? Okay, and then we want to look at these variables, X matrix, Y vector, samples, classes, etc. Right, so I'm going to switch over to the whiteboard. Oh, I need to stop sharing. Share. So this is actually really important, right? So you understanding how to take a problem and converting it into machine learning. So what I would say is I had a lot of questions in there, but find out the X and the Y. That's really the key thing. So these X and Y's represent data. Okay, that's what they represent. All right, so Y is usually the labels. So what are the labels here for this problem? What are we trying to do? Huh? So what are the labels? Gun, no gun, right? Simple. All right, so it's a binary problem. So let's say gun, not gun. That's what your machine learning algorithm needs to do. This, of course, will not be words, but it'll just be like numbers. So 0 and 1, for instance. Okay. You see that? This is important. All right. What about the X? What are the X values then? They're the data, right? So we give the model that, and it tells us if it has a gun or it doesn't have a gun. So what would we give it? Pictures, right? Images, exactly. So we have images here. So we can start to think images. All right, just to keep things simple, let's say that they're black and white, okay, instead of color images. They're usually on Facebook going to be really big images, probably. You know, people might be using 4K cameras, etc., right? So they're going to be really big images. However, machine learning algorithms currently don't work with really large images, so you need to downsample the images. There's a lot of libraries, and we will see a few of them later in the semester that allow us to do that, okay? You usually want your images to be of a specific size. So let's say that your images are, you know, let's say 2000 by 2000 pixels. That's too big. And so we would want to reduce those in size. This is recording, correct? You guys know? Yeah. All right. So we are going to reduce them in size. Now, something like MNIST, for instance, the classic data set, just to give you an example, is 28 by 28. Is it 28 by 28? I think it is. Is that 784? 28 by 28? 784? Yeah, okay. So MNIST, the classic data set, is that an image is that size. They're very small, okay? 32 by 32 is the retail MNIST, I think it's called. Forget the exact name. It's a little bit bigger, right? And those are color images. So that's a nice thing about that data set. So what's a recommended size nowadays for an image? Probably around no more, I would say, than 300 by 300. Because otherwise, you start to get into problems that your GPU just takes forever. You see what I'm saying? Or it runs out of memory, or, you know, so it makes your life miserable, right? And sometimes you don't need such a big image. Okay, so start smaller, and then you can always write your code in such a way that it's very easy just to say, okay, now make it 500 by 500. Let's see what happens. But start at, you know, 100 by 100. Okay, so this is important. Why is this important? Because this is the data, and the data needs to have dimensions, right? Everything in machine learning is dimensions. Okay, we need to know the dimensions. We need to know how many pixels it's going to have, because each one of those pixels is going to map to a weight in a neuron in the neural network. You see what I'm saying? So I jumped ahead there to just a class of algorithms called neural networks. So not everything that we will do is neural networks, obviously, but we want to make data sets that will run on everything. You know what I mean? And so we want to make a data set that will run on a neural network, or it'll run on something else. Okay, so this is what this is for. So we want to think in terms of X and Y. There's a couple of, now we have a problem here in the sense that the images are basically arrays, right? So they're basically like that, right? Let's say that the images are 300 by 300. Let's just go with that number. You have, and what that means is when you start to solve these problems, you need to start making assumptions, but they should be good assumptions, okay? That there's a range where you can go down or up, okay, in your assumptions. So there is that. So what does X and Y look like? Basically, the simplest thing is for it to be a matrix, like an Excel spreadsheet, right? So we can think of it as an Excel spreadsheet. So that means we have rows and columns. You see what I'm saying? Start there before you think of other more complex things, okay? Now this one is X, and this one is Y. So it's very easy already with Y, right? We know it's, well, we need to define what a row is, first of all. So I would say that you should define each row as a sample. So that's the terminology. And if I say a sample, what do I mean? An image. Why? Because for every image, we want to know gun, no gun, right? So we need to look at one, like over there, you guys can see all those pictures, right? On the wall. Perfect. There's one of Barack Obama. There's one of, I don't know what else. I can't. Some music covers, I think. And so are there any guns there? I don't know. But there might be, right? But one thing is they're all the same size, I think, right? That's really important and a high recommendation, right? Now, obviously on Facebook, people have different cameras, right? And so the images are not the same size. So I'm saying that's true. That's the reality of the world. However, as you feed those images into the machine learning algorithm, you want to make them all into the same size. You see that? You want it to be consistent. So there's going to be some tricks that we're going to have to learn about image processing on how to make an image, all the images, even though they're not the same size, into the same size. Sometimes that means corrupting the data a little bit or losing some data if you crop it, etc. Those are, again, assumptions that you have to make and you have to live with, okay? And so you want to definitely know all the techniques so that you can select the best ones. Got it? But in essence, all the pre-trained models, for instance, they all have fixed size. There's 300 by 300, and so you're going to have to downsize or crop or something like that. Anyway, so we've defined that a sample. So this case is easy because we've defined that a sample is basically an image. So it's not always so straightforward, right? And other problems. But in this one it is. So a sample is usually going to be a row, and it's usually going to be the thing that we're trying to predict something about. So in this case, it's an image. Now, if you notice, this is just a row like that, right? So given an image, now another thing that we need is to be able to train a machine learning algorithm, we need to have data that we use to train the model, right? And then we have other data that once we've trained the model, we apply the model to that data so that we can predict, right? And once we deploy the model, obviously we're going to get new images. We get a new image, on Facebook. They deploy this tool. You load an image, and then it's going to say gun, no gun. If there's a gun, it flags it probably. It says, violence, something like that. All right, so that's the idea. That's the goal. And so we need data for training and data for testing. That means that when we provide the image, we provide that it has a gun or not a gun. Because remember that what machine learning algorithms will do is they will learn to correlate this to that. That is to say, I have an image here with no gun, right? Then I have another image here with no gun. Then I have an image here with a gun. And I have an image here with a gun. And then finally, these two don't have guns. You see that? That's what the machine learning algorithm learns. It's the correlation. Why is it? What pattern do I see in the image that tells me there's a gun? So this has a pattern, and this one has a pattern. Should be one. These two have a pattern that, let me erase that. Okay. So these two have a pattern in the image that indicates, okay, there's a gun in it. And the other ones hopefully don't have it, and so there's no gun. Got it? So this is called supervised learning, or a classification problem, and you're learning how to correlate the data to the class. So you need to provide it. There are other techniques where you don't provide the labels, but then you can't use neural networks like this. You have to use other techniques, and they're not as accurate. Okay, got it? All right. So anyway, what we're doing right now is giving you word problems, right? And we'll do a few today, few word problems, and I'll follow this procedure. I'm trying to identify what X is, what Y is, and answer the questions that I made. All right, so now the key thing is dimension. We always want to think in terms of dimensions. And what I mean by that is, so I'm going to split this into two things because we treat X and Y as separate pretty much all the time. So usually our data set is like this, but then we're going to make it into two data sets. Or two objects, two variables, two tensors. So now I want you to answer always answer that. And this is obviously 1, because there's only 1 in this case. So, do we need any other information about the dimensions? N just means the number of rows, which also translates into the number of samples. M means something, which right now we can call it the columns, okay, for now. 1 is a column, and it has rows. How many rows does, and then this is X and this is Y, right? So this is X and this is Y. So how many rows does Y have? N, very good. They need to match. For every sample, we have a label, right? Either a 0 or 1. We already identified that the values are 0 or 1, gun, no gun. Now, what is N? The number of rows, which is the number samples. So that means how many images we're going to use to train our model. So how do we answer this question? Well, I said it was Facebook that was building this, right? How many images do you think they have to train that model? Millions, right? Many, exactly. So that's how you get that number. Now, if it was just you guys doing this at the university, how many images would you have? 1 million images? Probably not, right? Especially if you want an accurate model, what would you have to do? You would have to look at every single image with your own eyes and say gun, no gun, right? How many images do you think, how much time do you think it would take you to do that for 10,000 images? A lot of time. Do you see that? So those are the trade-offs, right? Accuracy will require a very well annotated data set. That's what that means, like providing the label, but that takes time. Now, if all of you looked at all the images, that you may create more, but it costs money, right? You have to pay people and things like that. So it's expensive. Anyway, for N, all you need to do in the problems is just provide some logical argument. Well, it's Facebook. They have a ton of images, so 1 million, something like that, or 10 million. So that's good enough. But see, this is what I want you to do. I want you to think of the problems. If I don't say Facebook, but I say you for a school project, then you could say 2,000. All right. Now, what is M? Columns, right? And that's something I probably haven't introduced. So that's going to be that term feature. Features usually in this context translate to columns. What that means is the features are the descriptors of the sample. Okay? Are the things that describe it. One thing that is very important about them is that because they are column, they need to be the same thing for every sample. Do you know what I mean by that? Let's say that this is column 101, right? Then for every sample, column 101 needs to be the same question, for instance. And the question could be like, does this have green colors, right? So for every sample, you would answer yes or no. Do you see that? About greenness. Or it doesn't have to be a binary question. It could be a value from 0 to 255. Green color, this is a 5, the other one's a 10, one is a 250. So what does that mean? One is darker green, one is lighter green. Do you see what I'm saying? So it doesn't have to be a binary, it can be any number, right? But it has to be, for every sample, column 101 is the same. Got it? Now that would be very hard, right? To create 1,000 features where it's questions about each image. Now you can do that, and that's called feature engineering, but it takes a lot of work, right? An easier solution is, because all the images have the same size, you see how that starts to become very useful, because if all the images have different sizes, this won't work. Why? Because the columns will not align. Do you see what I'm saying? But if they're all the same size, then they will align, and that's what's important. Okay, so let's go with the example that I'm very familiar with. Let's say that we make the images 28 by 28. So yeah, they're very blurry, but it may be good enough to find guns, right? So 28 by 28, because this is a one. Now think of the problem. This is two-dimensional, right? We're also ignoring color right now, and we're just saying that it's black and white. But this is a row, right? These are rows. And we want to just stay with the simplest approach right now. How do we fit images into a row? Because the images are two-dimensional arrays, right? And the rows are one-dimensional. The pixels, right? So the pixels are what then? The features? So that's the standard approach. So you're thinking, like, how do I do it? And I said, okay, you could engineer 1,000 features where you ask individual questions, but actually the simplest solution is just to use every pixel as a feature. So as long as all the images are the same size, you're good. Got it? Does that make sense? Okay. So how many pixels do we have in an image that is 28 by 28? 784. But how do we fit this image that is two-dimensional into a one-dimensional row? 784 features, right? So for lack of a better name, I call this spaghettifying, right? So the idea is you take the two-dimensional image like this, right? If you crochet or something, you probably have a sense of this. Like if you grab the thread from here and grab it from here and do this, right? You may make that whole thing into just one string, right? So it's almost like you're doing, imagine you take the first row and now you put it here. Then you grab the second row and you just concatenate it behind it, right? You see that? And then you do the same. You got the third row. And you dot, dot, dot until you've done every single one and add the last one. You guys see that? And so every row there that you concatenate them. So you have basically you made a two-dimensional array of 28 by 28 into a one vector of 784 without loss of information. Neural nets are smart enough, or other machine learning algorithms, that they're able to figure out the patterns. Even though for us humans, we see that if we were to see an image like that, we'd be confused, right? We would, because the way that it works, we need to see things differently. But the machine learning algorithms, to them, is fine. Got it? Does that make sense, guys? So that's actually, like, for images. I usually like to start with images because it's very intuitive. With images, this is the standard approach. And so the images here are 784. So then, now again, every image needs to be the same size. Okay, that's very important. So what is the number for M then? No, for M, what is the 784? Very good. Do you see this is nice? This is how you do machine learning, right? You start thinking of N's, M's, everything. And then once you do that, you'll see that it'll start to fit into the machine learning algorithms. Later on, we're going to do the classic MNIST and IRIS, and we're going to run them through machine learning algorithms. And by doing that and doing this, you're able to link them and understand then how do you take a new problem and load it in. Got it? Any questions? Yeah, please.
What do you think about
What if a picture has less than 784 pixels? Then you can add, which is called padding. I mean, you can't, it's not magic, right? So you have to make assumptions, you have to take decisions. But if you think that's an important image that you want in there, and everything else is 784, and those for some reason are smaller, pad it. Do padding. You know, you extend the background because it could be that it's a gun in a grass field, right? So just happens to be very small, so you add more grass. It doesn't change the fact that there's a gun there. See? So yeah.
So to review, X matrix refers to the sample data itself, Y refers to the label,
Yes.
and then M is the number of features.
M is the number of features, yes. Number of samples, yeah. Are you looking at the questions actually? Did you see if we covered all of them? So what were the questions? Let's see. That's actually a good point. So if you go to the document, right? What were the questions? Because you have to answer that for almost every problem. So what were they? Well, I have him here. I can look. So let's see. So stop sharing this. And I need to go here. All right. So the things we were looking at are, so again, right? So I've said that it's classification problems because not every machine learning problem will be classification. Sometimes I want you to tell me the temperature of a place, and that's not going to be hot or cold. It's going to be 72 degrees or 73 degrees. But in this case, we're doing classification. The X matrix, what was it for this example? Was N a million by M 784, right? So the rows are the samples, columns are the pixels. So we were able to do the X matrix, I would say. That's the data. Every row has a corresponding column or label, sorry, and that's in the Y vector. As you will see a lot in the code, this is very consistent pretty much every time we do this. We're going to have an X and a Y as two separate variables, if you will. What are the samples? So what is the sample? An image. Super easy. The classes, they were gun, no gun. That's 0 or 1. You'll see later how it could be -1 and 1, but it's convenient for it to be 0 and 1. Just because we could build a classifier that predicts from 0 to 1. So if it's less than 0.5, it's 0. If it's more than 0.5, it's 1. So we've got this is called a binary classifier. You can do that in a couple of ways, but that's a way of doing it. So what are the samples, images? What are the classes? 0 and gun. Define a set of features. What are the features? Pixels. How many? 784. You want to quantify. Define the dimensions of X and Y. They basically summarize everything. 1 million by 784. 1 million by 1. And indicate what they mean, you know, and that's that's it. So that's the other like homework that I will give you. I won't do all these problems, and some of them are harder. Like, let's do actually, yeah, we'll do one more. So I think, you know, we have plenty of time. And then I still don't start working on this yet. I may do a few more next week, and then I'll create either new ones or I'll modify them a little bit, okay? So let me think about it. But let's just, for now, I want you to get the gist. Now, not all of them will be the same. Some of them are difficult, are more complicated. Let's do I want to do number 3. So let me actually do this. Oops.